All right. Good evening, everyone. Welcome back from spring break. It's it's weird. It's light outside now, thanks to the time change when we start this class. So it feels weird saying evening, but it is still technically evening. A few reminders as well as some new information on our whiteboard before we begin our lecture, picking up where we left off with 3.8. So we finished 3.2 and 3.4 last class, so they are due today. Lots of time to get those done, so no excuses there. Hopefully everybody got everything done there. We will start and finish 3.8, so that's going to be due in a week on the 21st. We will also start and finish 4.1, but because I'm going to be giving you test 2, I want to give you a couple extra days on that homework. And it might not seem like a couple extra days since it's only 2 more days past the test, but you are still getting extra time ultimately. So hopefully you appreciate that. So again, we will start and finish both 3.8 and 4.1. 3.8 will be due on the 21st, giving you a break on 4.1, having it due the 25th. Test 2 is going to cover all of the sections from chapter 2 and 3 that have been and will be covered. 2.2, 2.3, 3.1, 3.2, 3.4, and 3.8. So 6 sections. It is going to be available for 3 days, and I will not be changing that. So that's Monday the 21st through Wednesday the 23rd. It will be due 11:59 p.m. the 23rd. This is going to work the same as last time. You're going to have to show all your work and submit it in Canvas within 15 minutes of finishing, not fishing. No notes, no books, no calculators. This is going to be an 18-question test. Some of the questions are a little longer, so I'm giving you 2 less questions on this one. Still 2 hours. Still 1 attempt. Make sure you show as much work as possible, and then you can email me and say, hey, Mr. Beckner, check out questions 1, 3, 5, 9, whatever. I think I deserve some partial credit, and then I can give you partial credit based on that. There is a review, just like for the first test, in the assignment section. It is immediately below homework for 3.8. The review will be similar to the test, so it's a good idea to complete the review. It is not going to be graded, though. The test will only be visible in my math lab those 3 days, the 21st to the 23rd, and it will be at the top of the page, probably the second assignment, probably right under test 2, but it will be available at the top. Make sure that you have 2 hours to start and finish it because you will have to do this in 1 sitting. This will be the last no calculator test, test 3, and the final will be, you will be allowed to have calculators, and those will be the proctored exams where you'll have to have either your cell phone or a laptop camera, or just a webcam, whatever, on you for the test that is required. If you don't have either of those things available, you're going to need to email me sooner than later so that we can work out a situation for you to take it in a testing environment, preferably at TCC, so that it doesn't cost you anything. So again, please be in communication with me sooner than later about that if you have absolutely zero access to some type of camera for test 3 and for the final exam. Okay, so with all that being said, let's go ahead and pick up where we left off. We had finished 3.4, so we're going to do 3.8, which is on implicit differentiation. We'll take about an hour to do that. Then we will start chapter 4.1, which is anti-differentiation, going backwards from what we're used to for the past 2 chapters. We'll make it about 20 minutes in, 25 minutes in, take a break, and then we'll finish it, and that'll be pretty much in the nick of time for our class for this evening. All right. As always, if you have any questions, hit me up in the chat.
Now, if you actually look at the title of the textbook says Implicit Differentiation and Logarithmic Differentiation. We're not going to do the logarithmic part. As I've said, there's a lot of material we have to trim out of this textbook. Some of it is we'll come back to it and do it later. That's not one of them. So we are only going to cover the implicit differentiation side of 3.8. The reason I said 3.6 previously is because the last textbook we had, it was called 3.6. That's what it says on my little paper notes. So my bad on that. But implicit differentiation. Up to this point, we have been doing explicit differentiation. Differentiation. There we go. I don't mean explicit as in, explicit content. This is a CD you can't buy without parental units with you. Explicit means direct. Implicit means kind of indirect. Sometimes people say explicit is more obvious, implicit is more implied. There's a couple different ways you can interpret these words. So up until this point, we have been doing explicit differentiation. Let me not do a period, let me do a comma, which is used when there is only one independent variable. So just an x or just a y, etc. You can't have x's and y's. Now, in that last section, we started having formulas that we wanted to take derivatives of that had multiple variables, and we said, well, for now at least, we need to take one of those variables and put it in terms of the other. Well, now we're going to learn a way that we don't necessarily have to do that. For the optimization problems, it's still the best way to do things. This is going to be used for another setup that we'll see examples for, obviously. So when you have mixed variables, an x and a y, or an x and a z or anything, in an equation, implicit differentiation is a possible way to find an exact derivative. Implicit differentiation is based on the chain rule. Give you a second to get that. Okay. Chain rule states take d dx of both sides, sorry, not of both sides. Chain rule states that if you take d dx of a compound function, then the derivative is the derivative of the outside times the derivative of the inside. That's just a quick reminder of the chain rule. Even though you may not be able to solve for, say, y as a function of x, it can still be thought of that way. I.e., y could be considered a compound function. For example, the equation of a circle radius 5 is as follows. x squared plus y squared equals 25. This equation cannot be solved for y and expressed as a function x because of the plus or minus square root property. If you solve this for y, if you try and solve this for y, you'll subtract x squared on both sides. I'm just going to show you really quickly. X squared plus y squared equals 25. Subtract x squared on both sides, you get y squared equals 25 minus x squared. Then you take the plus or minus square root of both sides to get y equals plus or minus square root of 25 minus x squared. But because of the plus or minus, this is not a function. So you can't write y as f of x. We can't say y is f of x because of that plus or minus. It's not possible to explicitly define y as a function of x, even though it kind of is. It's got this kind of thing going on because sometimes it's positive, sometimes it's negative. It's actually both all the time. Let's say sometimes. Because this is the equation of a circle. It's a perfectly fine graph, but when you go to graph it, this is what it looks like. Here's your radius of 5. It fails the vertical line test miserably. Circles are not functions, so when you try and solve it for y, you can't do that because the plus or minus thing makes it not a function. We discussed that in pre-calc 1. So again, that's when this can be helpful. If I wanted to find the derivative of this thing, dy dx, you'd say, oh, well, first solve it for y and then take the derivative, but you can't solve this for y and take a derivative because it's not a functions, and you can only take derivatives traditionally of functions. So that's the explicit side of things. Now we're going implicit, and we do this kind of chain rule thing. So how does this work? What's the actual point of this? Basically, to apply the chain rule in this implicit differentiation method, if you take a derivative, good, of a variable, that is, and I'm going to underline this and caps it, not same letter, no more caps, as what you are differentiating. Back to. You need a dy over dx. In the term. Whatever letters are being used. It doesn't have to be y and x, it could be a and b, z and q, whatever. The variable on the bottom is what you're taking the derivative with respect to. The variable on the top is what you're trying to say the original function was. This right here is the derivative of the inside. So again, whenever you take a derivative of a variable that's not the same as the letters what you're differentiating with respect to. So this circle is the first one we're going to do. And I'm going to ask us to find dy dx, which means we're finding the derivative of y with respect to x. So when we're doing derivatives, we're treating the x as the regular input, But whenever we go to take a derivative of a y, we would have to throw this extra dy dx in. That's kind of like the derivative of the inside, because this y, yeah, it can arguably be solved for something, but we're not explicitly writing it. So there's an inside, so the dy dx counts as the derivative of the inside. Just saying the derivative of y squared is 2y would be the derivative of the outside. But we're not actually going to take the derivatives of the inside. We're ultimately going to solve for it. It feels a little weird at first. So again, all this said and done, the important part is right here. If you're taking a derivative with respect to x, anytime you see a y or a z or an a or a b, you're going to have to throw that dy dx in, or dA dx or dz dx. But whenever you take a derivative of an x term, everything is normal. Okay, example 1. A. And do I need to write A? I don't need to write A, just example 1. If, let me just write the whole thing. If x squared plus y squared is equal to 25, this is the equation we're dealing with. Find dy dx. We are finding the slope of this function at any point. That's what we're doing. Dy dx is always slope. That's the interpretation. The rate of change of y with respect to x, that's y2 minus y1 over x2 minus x1 as we get super close to each other. If you do dx dy, that's not slope. That's the reciprocal of slope, in fact. So again, we're basically trying to find these slopes. So we're going to take the derivative of both sides. And whenever we don't match them, why am I all the way back up here? Whenever they don't match, you do this extra chaining. So what do? We take d dx of both sides. That's going to be us taking our derivative. Anytime you're taking a derivative, that's the same thing we've been doing before. Take a derivative of both sides. So we go d dx of the x squared plus y squared equals d dx of the 25. And yeah, you probably don't need to put the 25 in parentheses, but I'm just being consistent. Again, when we went back in the last section, we were doing a prime, we were technically taking the derivative of both sides. It's just when you're solved for a variable, there's no real need to show the work, it feels like, because it automatically falls down to dA dx or whatever it might be. Okay, so I'm going to show the work in blue. For this x squared, we're saying, what's the derivative of x squared? Well, the derivative of x squared is 2x. These letters match, so this is normal. There's nothing new there. The derivative of x squared is 2x. No surprise. Plus. Now this letter and this letter do not match, so we need implicit differentiation for the second term. You need the implicit differentiation for the y squared. All right, so let's just imagine they did match. What would the derivative of y squared be? It would be 2y. Bring the 2 out front, decrease the exponent by 1. The fact that it's a different letter doesn't affect that part. That's the, quote, derivative of the outside. But because this letter does not match this letter, we have to chain it, because y, we're saying it's a function of x. Even though we're not solving for it, it could be, in theory, a function of x potentially. If it can't be, then you don't ever do it that way, and that's why we just imply it. So the derivative of the inside, y being a function of x, would be dy dx. Because y is the substitution variable in that instance that we're not seeing. back up here. Y is really this thing, so we're taking the derivative of that with respect to x. This is the inside. But again, it's not really a function, so we can't use it. So this is us pretending like we took that derivative, and then equals, the derivative of 25 is 0. The derivative of a constant is always 0. So again, the only new weird thing here is this part. And again, that's under the basically. Because this letter, I know I'm repeating myself a lot, but this is weird. Doesn't match this letter. We are chaining. We're considering the y as an implicit function, a function of x as well, even though we can't technically write it that way. So here was the derivative of the outside, the 2y. Here's the derivative of the inside, y equals blah, blah, blah. Well, dy dx. Again, we can't find it directly, so that's all we can do. Now we're supposed to be finding dy dx. Well, guess what? In the process, that popped up naturally. There can actually be several of them. That's always possible, and we will see it. All we got to do from here is solve for dy dx using our basic algebra skills. Let's subtract the 2x on both sides. I'll show the work since it has that weird thing, which will give us 2y times dy over dx equals negative 2x. Then we're going to divide both sides by the 2y. Remember, we're trying to solve for this thing right here. We just got to get rid of the 2y. When we do that, we go over here. The 2y's cancel. You get dy over dx on the left. On the right, the 2's cancel, and you get negative x over y. This is fascinating, even though the original thing is not a function, we can still take the derivative as if it were a function and get this relationship. Now, I'm not claiming that the derivative is a function. I'm not making that claim. I'm just saying that we can take a derivative of something that's not a function and actually get an answer. And this doesn't have to be a function. It's not explicit. It doesn't say y equals. It's definitely not a function of one variable. It's a function of two variables. Now, you might say, well, Mr. Beckner, if I know what y is, I could plug it in. But again, we can't say that y is anything because it's actually two things. This is the best you can do for this problem. There are problems that you could, in theory, plug the y in there and get a different looking answer, but that's the best we can do for now. For this problem, it's all we can do. Oh, I know, this was supposed to be a part A. Now I remember why. So everything we just did was part A. Part B coming up, we're actually going to go and talk about that slope stuff I was referencing. Find the slope of the tangent curve at the points 0, 5, 3, 4, and 5, 0. Now, two of these I could pull up the graph and know instantly. 0, 5 and 5, 0. Those are super easy to tell graphically. Let's just do that to the side. Here's our slightly weird looking circle. All of these are 5s and negative 5s on the ends. So the 3 points I have labeled are 0, 5, which is right here, 5, 0, which is right here. That's the first and the third. And then 3, 4, which is somewhere about here. Now at the 0, 5 at the top one, this is what the tangent line would have to look like. That slope is 0. So we should be able to prove that with the calculus. This point over here at 5, 0, that would be a horizontal tangent, that would be a vertical tangent line. And that slope would be undefined because vertical lines have an undefined slope. And then this one in the middle, you can't actually see the numerical value of it. Let me just draw that circle, just that single point. There's the point 3, 4. There's the tangent line. You can't tell the number, but it's at least negative. You can tell it's negative and not positive. So let's see if the calculus agrees with that. So again, we know dy over dx, which is the slope function, is negative x over y. We're just going to plug these 3 points independently. So for the first case, at 0, 5, dy dx would be negative 0 over 5. Just plugging in the x and the y values. That's the x, that's the y value, which is 0. And look at that. The slope at 0, 5 graphically said it should be 0. That's good. Let's do the 5, 0 next. The ones that are easy to tell. That says dy over dx is equal to negative x over y, which is negative 5 over 0, and anything divided by 0 is undefined. Look at that. That point, graphically, it says it's an undefined slope. And at the point 3, 4, some random value in between those two, our dy dx, our slope, would be negative x over y, so negative 3 over 4, and that's at least a negative, so that sounds good. I can't really judge the size of it. I would say that doesn't look like a super steep line. It looks like it's pretty close to 1 if I'm drawing that to scale, and that number is pretty close to 1, more specifically negative 1. The closer and closer you get to that 5, 0, though, this slope is going to go to like negative 10, negative a million, negative 10 trillion, until it goes undefined. So even though we cannot write a circle as y equals, we can still find the slope along the curve but using implicit differentiation. Even though we can't solve for y, in general, for the functions you're given 100% of the time, even though we weren't given this thing as solve for y, we're still able to solve for dy dx. And that's just because these terms tend to pop out 1 or 2 at a time. They don't end up being squared or cubed or to the 4th power, any funky business. So it's, in general, easy to solve these, at least for polynomials. So I love this circle problem. It's one of my favorites because it's easy to judge, it's easy to graph, it's easy to see the analytics to it. Once again, on the analytics side, what was the weird part? What's this implicit differentiation? We'll tell you how you have to take the derivative. You have to be told to find dy dx or dz dx or dx dy. You have to be told which to do. And then the bottom letter tells you when things get weird or not. When the bottom letter matches the thing you're taking the derivative of, it's normal. When they don't match, you have to throw in an extra term. And this dy dx, you could also just call that y prime. So instead of going 2x plus 2y dy dx equals 0, we could go 2x plus 2y times y prime equals 0, and then still subtract the 2x and divide by the 2y. Whoa, that was weird. I must have been scrolling when I was writing. So dot, 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 you end up with y prime equals negative x over y. The same thing. But some people will goof up when they have a y next to a y prime and try and turn that into a y squared. Oh, there's a 1 implied here. 1 plus 1 is 2. No, this is not a 1. That represents a derivative. So make sure you're using the notation that you're comfortable with. I don't care which notation you use. I just make sure, I only care that you are comfortable using it. So make sure you know which one you're comfortable with using. All right, enough ranting. Let's do another finally, and no part A or B this time, just example 2. So if, this one will be a little more involved, y to the 4th plus x to the 4th minus 2x squared y squared equals 9. Find dy dx, or y prime, however you want to write that. I think it's a better idea to use the dy dx's because then you can tell when the variable, the independent variable doesn't match the with respect to variable. So my preference is this one, at least initially for my students. I will admit, me on my own, I use prime notation because it's less writing, but I've done 1,000 of these, so I'm a little more careful. So what do? We take d dx of both sides. We take the derivative of both sides. How do I know to take d dx? Because this was an x, this is an x. If I said to find dx dy, I'd be taking d dy on both sides. So we go d dx of all that jazz, and then d dx of the 9 like so. Now, when the letters don't match, you throw in that extra dy dx into the term. That's the chain effect. That's the derivative of the inside. That's going to happen immediately. These letters don't match, so we'll need to chain this. So the regular derivative of y to the fourth will be 4y cubed. If this letter on the bottom was a y, this is all it would be, but they don't match, so we have to chain it. So we go times. And it's always the derivative of this thing, and then the dx is obviously the bottom. The bottom is always the same. That's going to be dx because that's dx. Because this was a y, that's why this is dy. If this letter had been a z, it'd be dz over dx. If this letter had been an a, it would be dA over dx. If the letter on the bottom was a q, it would be dy over dq. Derivative of the outside times derivative of the inside, plus x to the fourth, that matches our with respect to variable, so that's just 4x cubed. No funny business there. Now here's where things get interesting. X squared times y squared is a product rule. That's a product. So we got to remember derivative first times second plus second times derivative. I think I said that wrong. First times derivative of the second plus second times derivative of the first, or whatever variation you like. Now that -2 is going to get annoying to have to deal with along the way. So I'm going to go -2 and then open a parentheses. And then inside of this parentheses will be the product rule. This x squared y squared is a product. That's why we have to treat it so. And not only is it a product, it's a product of different variables, so one of them is going to get this implicit style differentiation. But I'm leaving the -2 in front of everything. Now, I like to go I like to go second times derivative of the first, excuse me. But I'm just going to write them in the opposite order. So the first times the derivative of the second. So the first is the x squared. The derivative of the second, the derivative of y squared. Sorry, I got lost in translation for a second. So the x squared, I use the first, which means I'm going to use the derivative of the y squared. The derivative of y squared is 2y, but those letters don't match, y, x. So we need the additional dy over dx. Again, I took the first times the derivative of the second. So the first was the x squared. The second is the y squared. The derivative of the first is 2x. The derivative of the second is 2y dy dx because of the lack of matching variables with the with respect to part. So that was the first times the derivative of the second, then plus, we're going to do the derivative of the first times the second. The derivative of the first is 2x, no implicit needed, times the second is the y squared. See, the dy dx only pops up in one of those in the product rule because only one of those products didn't have a matching variable. So again, this was plus the derivative of the first times the second. That's the order I did. Equals, don't forget the right-hand side, equals the derivative of 9 is 0. Now what we need to do is ultimately solve for dy dx. First, let's distribute the -2 that's here. So we'll get 4y cubed dy dx plus 4x cubed minus, now there's already 2's in each of these, so that's going to be a -4 x squared y dy over dx, and no, these x's don't cancel, -4 xy squared equals 0. Now, the first problem we did, example 1, when we did that implicit derivative, there was only a single dy dx, so it was very easy to solve for. If you can't do that algebra, I'm terrified. I really am. I'm not trying to be mean. This is much more complicated, but in pre-calculus, you were taught these methods. The dy dx is here, and it's here. Now, if these were combinable, we could just say 4 plus 6 is 10, but they're not, because that's a 4y cubed in front of it, a -4x squared y in front of it. So they're not combinable. So instead, we have to take that alternative approach, which was to, come on, let me type just a little lower. Don't make me go to the next page. I'll write it. I'll write it. Move all terms with dy dx to one side, all others to the other side. Anything that has the dy dx, or y prime if you prefer, needs to stay on one side, everything else goes on the other. Now, I don't actually have to move any of the dy dx's because they're all on the same side. That doesn't have to be the case. They're both on the left. So the things that we need to move, this 4x cubed doesn't have it, and this -4x y squared doesn't have it. So they've got to move. To move the 4x cubed, you'll subtract. To move the -4x y squared, you will add. So what we get is 4y cubed times dy dx minus 4x squared y dy dx equals, and I'll show the ones that I moved in red. So again, they just change signs. The 4x cubed becomes -4x cubed because of subtraction. This minus becomes a plus, 4xy squared. You could have written the positive term first, it doesn't matter. Now what we're going to do is factor the GCF of dy dx out. Everything on the left has the dy dx, which means it's a common factor. That was weird. Why did it go away? So we can factor that out as a GCF. So we go dy dx, open parentheses. We're left with 4y cubed from the first one minus 4x squared y from the second one. And that will be equal to, I'm going to go ahead and swap the order of those just to get the positive term first. 4xy squared minus 4x cubed. And then we just divide by the thing next to the dy dx, divide by the parentheses. I'll show that step. Divide both sides by 4y cubed minus 4x squared y. Giving us our final answer, maybe, of dy over dx equals 4x y squared minus 4x cubed over 4y cubed minus 4x squared y. Now, what some people will think is that this is the answer. The answer, excuse me. But it's not. because this is simplifiable. And it's not out of your realm of what you should know how to simplify. When you've got big crazy fractions, if they've all got something in common, you can take it out. Well, there's GCFs in the top and the bottom, so that might be helpful. Let's do GCFs first. So we get dy dx. How are we on time? Okay. dy over dx. Ooh, that was weird. Equals. There's a GCF of 4x in the top. Open a parentheses. You'll be left with y squared from the first term minus, and then just a single, excuse me, then an x squared from the second one, not a single one. In the bottom, there's a GCF of 4y. And when you factor that out, when you take 4 and y from the first term, you'll still have 2 of those y's left over, so that's a y squared minus. When you take the 4 and the y from this one, you still have the x squared. And what's unbelievable is that those two parentheses match, so they can cancel, and we get dy over dx. Again, this and this will cancel. Also, the 4's cancel. Everything goes away except the x and the y. So the slope formula, the slope function for this crazy original function we had all the way back here, y to the fourth plus x to the fourth minus 2x squared y squared equals 9. The derivative of this thing with respect to x, in other words, its slope function, is just x over y. How in the heck did that happen to be so simple? Does it always turn out to be that simple? No. But this one was very simple for one particular reason, and I want to show you why. This is fun. Notice the similarity of the slope to this in comparison to the slope of the previous one. It's negative x over y versus positive x over y. Let me show you why that is. So just kind of a observation. Start with a circle, radius 3, which that would be x squared plus y squared equals 9. It's always x squared plus y squared equals the radius squared. I'm sorry, not a radius of 3, a radius of square root of 3. So if the radius is the square root of 3, the right side is the square root of 3 squared, which is 3. Now let's just square both sides of this. So you get x squared plus y squared squared equals 3 squared. Well, that's x squared plus y squared times x squared plus y squared equals 9. And then FOIL this out. We're just having fun here. This is not something I'm gonna ever ask you to do homework or test. This is just us having fun for a minute. If you FOIL this out, you'll get x squared, I'm sorry, x to the fourth. X squared times x squared is x to the fourth. That's the first. The outer would be a plus x squared times y squared. The inner would be the same thing, x squared y squared. And the last would be a plus y to the fourth, and then that's equal to a 9. Combine like terms, the middle, that's like a plus a, so 2a, but it's x to the fourth plus 2x squared y squared plus y to the fourth equals 9. Look at how similar this is to the original function, not the original function, the original equation I gave you. It's just a minus here instead of a plus. What that says is this is actually really, 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 really similar to just having an equation of a circle and squaring both sides. There's a very strong correlation there. And the derivative of the circle was negative x over y. It's just squaring two sides of an equation doesn't do anything to the actual equation. Just squaring both sides. Remember, whatever you do to one side of an equation, as long as you do to the other, you're not changing anything. So this thing should have the same slope as before I squared it. Again, because that was just an algebraic manipulation. So the slope of this thing should be the slope of this thing. And it's this middle term being positive instead of negative that is what causes the sign change. You could also argue that the squaring could have that effect, but it's really this term. So we just took an equation of a circle, squared both sides, and we got basically the same thing. So this is basically 1s, just a circle. It's just a circle that's been squared on both sides. If you graph x to the fourth plus 2x squared y squared plus y to the fourth equals 9, it would be a circle with a radius of square root of 3. That is why, after all the algebra was said and done, this derivative mirrored it so well. But again, it was that one teeny little sign change. If I put a plus there, then this would have been a negative instead. That's the only effect that it would have had. If I had made this a plus originally, then this derivative would have been a negative and it would have correlated 100%. But I wanted just to do a subtle difference there, literally. Pun intended. All right. Thought I had another one, but I'm not seeing, my papers got shuffled for reasons. Yeah, I'm not seeing my third example. Let's make up one. Insert page. There we go. That I tell you, this program, it does some weird, wacky things sometimes. I know occasionally it's my fault, but it's unpredictable often. Let's do e to the 2y. So we're gonna say if e to the 2y plus x is equal to the ln of y, find dy dx. So we're going to take the derivative of both sides. We're going to take dy, oh, yeah, this is about to crash. That I was right. This thing was being wacky. Give me enough time to finish. Please. And the annoying thing is if this crashes, I'm going to have to reload. That might not even be there. Come on. All right. All right, let's try Control Delete. Isn't technology fun? Oh, there it was. It was just fixing itself. Timing. Sorry, that's a, I don't know why I just said an inside joke. That was silly of me. Was it this one? Nope. There we go. How much did it save? How much did it save? Holy cow. It saved most of it. All right, insert new page. Example 3. If, what did I say? I was going to do e to the 2y plus x equals ln y. I think that's what I came up with. Find dy dx, aka y prime. So we take d dx at both sides, and it thought I'm on orange still. So d dx of the left, d dx of the right. E to the 2y plus x on the left, ln of y on the right. Oh, look, derivatives of exponentials and logarithms. You got to remember those formulas. They don't ever go away. So the derivative of e to the 2y, remember, the derivative of an exponential is the exponential times the derivative of the inside. So that's going to be e to the 2y, that's the exponential itself, times the derivative of the exponent itself. The derivative of 2y would normally just be a 2, but because these letters don't match, you have to throw in that dy dx. So again, the derivative, sorry, the original exponential times the derivative of the exponent, but the derivative of the exponent, this letter did not match that letter, which is why there's a dy dx. Plus the derivative of x, these letters do match, so just take a normal old derivative, which is 1, equals. These don't match, so you'll need a dy dx times whatever it is. Let's go ahead and put that there. What's the derivative of the natural log of y? It's 1 over y. Again, that's a formula you're supposed to know for this test. Both of those. It's just been a couple classes since we used them. Well, we got dy dx's on both sides. We can solve for them. And I'm going to have to go through a little quick since this thing froze and ate my time. So let's collect. Let's first reorder this just a little prettier. So that's 2 e to the 2y times y prime, or dy over dx, plus 1, equals 1 over y times dy over dx. Let's move the dy dx's left. That's my choice. If you want to move them right, you can. So I'm going to move this term to the, actually, I'm going to take that back. I usually move the dy dx's to the left, but I'm not going to this time because the only non-dy dx term is here on the left, so it's going to be easier for us just to move this term to the right. I know it looks like a Madden drawing now. So we're going to move this term. I'll show that because I'm going back on what I said. 2e to the 2y, we're going to subtract that on both sides. So that's going to give us 1 equals 1 over y dy over dx minus 2e to the 2y dy over dx. Take our GCF out. So we get 1 equals dy over dx, parentheses. 1 over y is what we're left from the first term, minus 2e to the 2y is what we're left with from the second term. And then we just divide by the parentheses. So we're going to divide the 1 by that parentheses. We're going to divide by the dy dx by the parentheses. What we get is 1 over y minus 2e to the 2y is equal to dy dx. This is not in an okay format for the answer because it's a compound fraction. The easiest way to simplify these, the only denominator inside of the fraction is a 1, so you multiply all tops by the LCD, which is y. Because this is a y and it's the only denominator, you're going to multiply the 1, and this thing by a y. Why is that doing that to me? Stop it. So I will show that in color. We're multiplying the top one by a y, this one by a y, and this thing by a y. And that's still equal to our dy over dx. The reason we do that is so these y's cancel right here. We want those to go away so there is no more compound fraction. So what we get for our final answer in the top is just a y over. The bottom left is now just a 1 minus, let's put that y up next to the 2 and e to the 2y. That got really sloppy. dy over dx. There is our slope formula. That one's a little more intense algebraically because of the compound fraction part. It's also a little more intense calculus-wise because you have to remember all your derivative rules that your teacher told you had to remember all of. But if you put all that together along with the algebra we did in that last example, it's not too terrible. So again, we had an equation that you cannot explicitly solve for y. Even the best mathematicians analytically cannot solve this for y because one of the y's is up in an exponential and the other's in a logarithm. That is insane. But even though we can't explicitly solve this for y, even if it is a function, even if it's a function that we can't solve for y, we can still find its derivative. It just happens to be that the derivative has some y's and x's in it potentially. It's interesting, it doesn't even have any x's. The derivative is entirely dependent on the y value, not on the x value at all. So if you graph this thing, the left and right position doesn't even affect the slope. It's only affected by the vertical position. It's kind of fascinating. That, I believe, should be the end of 3.8. All right, daily notes. Scroll down, just ignore that stuff. Yeah, we're good. So we finished 3.8, so that should also be due on 7.2.
Ignore that last part, obviously. I just got back to my computer about 5 seconds too late after letting my dog out. All right, so that closed up with that. So give me 5 seconds and we will get our video starting 4.1. All right, and I just wanted to remind you the actual dates for the test since we just finished the material in the sections 2.2, 2.3, 3.1, 3.2, 3.4, 3.8. That's going to be available the 21st to the 23rd. So that's a week from today, the Monday through Wednesday, due on 11:59 p.m. that Wednesday. 18 questions, 2 hours, no notes, no books, no calculators. It'll be the last no calculator test. You'll show your work and submit it in Canvas just like last time. Email me mentioning any necessary partial credit. And I think it should all be the same as last time, so it shouldn't be any confusion. I just want to make sure to bring that up because I know a few people came in a little bit late. All right, so we finished chapter 3. Now let's get into 4.1, chapter 4, which again is the opposite of differentiation. We call it anti-differentiation, and it'll have another name known as integration along the way as well. But here we go.
And with this chapter, just like the last couple chapters, we will kind of piecemeal this together. We won't necessarily cover every single topic. For instance, 4.2, we're going to use as an introduction to a concept, but I'm not going to assign you formal homework on 4.2, and I don't anticipate testing you on 4.2. But but the concept of 4.2 is important. So I'm still going to cover it as a concept, but moving forward, the problems are extremely time consuming to do in that manner. So I just don't really see the need to do it in this course. Again, unless we have time to come back to it at the end. And as many times as I've said that, you know, we're not going to be able to come back to all these topics. So anti-differentiation. Another word for anti-differentiation means anti-derivative. It means the opposite of a derivative, anti-opposite, anti-opposite. So an antiderivative, opposite process finding a derivative. So I've alluded to this before. I've said there are three main topics in this course: limits, derivatives, and antiderivatives. There is another word for anti-differentiation and antiderivatives. Don't you love math people? It's not just us. It's science people in general. They like to have multiple words for things. And believe it or not, it's not just them as well. The English people, oh man, they got 50 words for different things, right? Synonyms and homonyms, oh my, all that good stuff. So one more word for this stuff is integral. Integrals are antiderivatives. They are the process of anti-differentiation. So we define lowercase w and an n before that. We define the indefinite integral as the antiderivative of some function f of x. So up until now, if I gave you the function x squared, you could find its derivative, and it would be 2x. Now what we're going to be doing is going backwards. Now, with anti-differentiation, with antiderivatives, with integration, you'd start with the 2x, and you'd say, okay, what's the antiderivative, or what's the integral? And then you'd say x squared, because they're just going backwards. If x squared has a derivative of 2x, then 2x has an antiderivative of x squared, ... There's actually some more to it than just that, and we will see why that is soon enough. But if you start with one function and you take its derivative to get a second function, then if you start with the second function and antiderivative it, you get the first function, basically. So, notation. This is important. If you're given some f of x, so given some function, this is the symbol for an integral, or this is the symbol for an antiderivative, or anti-differentiation, whatever you want to call it. This represents the integral of a function. So the integral of f of x times dx. What is this thing? Just go with it for a minute, we'll get into it. But really, this right here is all we're really worried about. This dx is just always going to be sitting there. So the integral of some little f of x, we tend to denote this with a capital letter. You don't have to, but this is typical. But then there's also this, plus a c, where the c is a constant. So I'm just going to flat out give this to you and then explain why. So the integral of some function, and again, this is just an extra little detail, kind of like dy dx is a derivative. This is just part of the integration process. You got to get used to the symbols. Again, this is really what we're focusing on. And this symbol, this little like snake looking S thing on the left and a dx on the right, that's us to do an integration, to integrate, to derive, whatever you want to call it. It would be equal to some function plus a constant. Some function plus a constant. But this is if and only if. IFF This means if and only if. Mathematicians love this phrase because it means it's a two-way street, not just a one-way street. If is only a one-way street. If and only if is a two-way street. It means it works both ways. So if and only if the derivative of the thing on the right is equal to the thing on the left. So again, just kind of making a note here. Usually denote the integral with a capital letter of the original. Typical, doesn't have to be. I could say, instead of writing the capital F, I could write a G, a lowercase g even. But then this would be a lowercase g prime equals f of x. So the integral of function 1 is equal to function 2 only, so if and only if, the derivative of function 2 is function 1. The integral of function 1 is equal to function 2 if and only if the derivative of function 2 is function 1. Let's try this out. So, for example, the function f of x equals x squared, let's go back to what we were talking about earlier, has a derivative of f prime of x is equal to 2x. That's just using the straight up power rule, which you should all know, should all be embedded in your brains from now until eternity. Drop the exponent down, then decrease it by 1. So if we start out with the function x squared, its derivative is 2x. This says, or so, the antiderivative integral of some function 2x of this function is f of x equals x squared and then plus c. Now, I didn't use the capital letter this time because I already was using the prime notation. I was showing function, derivative. So here's the original derivative, and then here's the original function. So if I wanted to just switch the letters, I could say it. Or if I called g of x equal to 2x, then capital G of x, this is the integral of 2x dx, which is x squared, plus this constant. Again, derivative going from x squared, you get 2x. If you go backwards, starting with 2x, you get x squared, but then there's this extra constant in there. But why is c there? I don't have enough space for the question mark. Let me do this. Why is there a constant there? Some number, a 5, a 12, a 39, a negative a million, pi. It's just saying that some number is going to be there, potentially. Check this out. Let's say your original lowercase function is x squared plus 9. This has a derivative of f prime of x equals 2x. Say f of x equals x squared plus 100. This has a derivative of f prime of x equals 2x. Say your function was x squared plus 209,111. The derivative of that is still just 2x. Notice when you take a derivative of a constant, it goes away. So, all right, before we get to the so, if your function was x squared, its derivative is 2x. If your function is x squared plus 9, its derivative is 2x. If your function is x squared plus 100, x squared plus a million, x squared plus 209,111, all of them have the exact same derivative. So when you're working backwards, if you've got the derivative and you're doing an antiderivative, we know that the 2x leads to an x squared. Because, I mean, just look, every time we've had x squared, it led to 2x. So going backwards, 2x leads to x squared. But how do we know whether it has the 9, the 100, the 209,000, a million, or nothing? We can't, let me type this part. I'm getting sick of that. We can't tell what the antiderivative has for a constant based on the original derivative, because when you take a derivative of a constant, it is 0. This is why we have the plus c. That plus c just denotes that, hey, at least for now, given the information we've talked about thus far, when you go to do the antiderivative, you can't say definitively for now whether that function had a 9 at the end, or 100 at the end, or a 209,000 at the end, or nothing at the end. So you just put a generic plus c in there to say, hey, we don't know what the number is, but maybe we could find it later. Maybe there's a way that we can find that later. And by maybe, I mean there's definitely a way we can find it later. Now here's what sucks. In your homework, if you forget the plus c, it's wrong. On a test, if you forget the plus c, it's wrong, but if you show your work, I could go back and give you partial credit. Now remember, this is test 3 material, so don't focus on this too much for now. But again, without a plus c, your answers are wrong, and you'd have to come back and say, if it was a test, hey, check out my work. I had the main part of the antiderivative correct. I just forgot my plus c. Okay. Now, before we go to just going and giving you the power rule for integration, the power rule for anti-differentiation, those are the same thing. There was a power rule for derivatives, and there's a power rule for going backwards. But instead of going through and doing a proof of this, which we can't do proofs of antiderivatives in here, it's kind of crazy. So we're not going to worry about that aspect. But what we will do is try and find a pattern. So let's see if we can identify what a formula for a power rule look like by doing derivatives. So let's say if f of x, we already saw x squared led to 2x. So with a function of x squared, the derivative is 2x. With a function of x cubed, the derivative is 3x squared. With a function of x to the fourth, its derivative would be 3x to the third. With a function, let's skip x to the fifth, let's just go straight to like x to the eighth. Its derivative would be 8 times x to the seventh. Because when we go take a derivative, we bring the exponent down and decrease its exponent by 1. So doing derivatives, bring the exponent down, and then decrease the original exponent by 1. We're going backwards. Going backwards, in other words, anti-derivative, backwards, not words, we need to do the opposite of these things. So we expect the exponent to increase by 1, and we need to eliminate the coefficient that may have been the original exponent via division. So again, imagine yourself going from the 2x to the x squared. What's happened? The x had an exponent of a 1 and it goes to 2. How about this one? The x cubed goes to a 4. The x squared goes to a 3. The x to the 7th goes to an 8. So going backwards, each of these exponents is going to increase by 1. Instead of decreasing by 1, we're now going to increase by 1 because we're going backwards. Okay, well, how about the rest? Because let's go back to derivative mindset. With the x squared, the 2 drops down. With the x to the 4th, I wrote a 4 here. No one said anything, and that's okay. This is supposed to be a 4. 4, not 3. Let me erase that. If anyone wrote that, I'm sorry. Bring the exponent down, which was a 4. That was me rushing. And then decrease the exponent by 1, so 4 to 3. So with a derivative of 2x, the antiderivative is x squared. The 2's gone. But you can't get rid of this 2 by addition or subtraction. You got to get rid of it by multiplication or division. Well, it feels like it multiplied one way, so now to go backwards, we divide. So we'd have to divide it by 2. Or this one, we'd have to divide by 3 to get rid of the 3. This one, you'd have to divide by 4 to get rid of the 4. This one, you'd have to divide by 8 to get rid of the 8. How do we know what we're dividing by? We're dividing by what the future exponent is. So again, in order to get rid of this 2, you divide by 2, which is the next up exponent. To get rid of this 3, we divide by 3, which would be the next up exponent. To get rid of this 4, we divide by 4, which is this exponent plus 1. Divide by 8, so there's no 8 here anymore, which should have been 7 plus 1. This is what leads us to our formula by just observation. So, power rule for integration. Let's put all of that together. The integral. So this is the symbol for integral. And if you want to make it nice and pretty, oops, too much. It looks like that. When you're doing your work, if you're anything like me, they end up looking more like S's, and that's okay, like a backwards S, if you will. I don't know why I said backwards S. What am I thinking? Ignore what I just said. If I didn't mention this at the beginning of class, I'm teaching with one eye open right now. I've scratched my cornea. It's a lot of fun. So I might make 1 or 2 more mistakes than usual. Doing my best. Okay. So that's our integration symbol. Then the thing that you're actually going to go backwards on goes here, and then at the end is a dx. So we're doing a power rule, so that's an x to the m. Just like when we did a power rule for derivatives, it was the derivative d dx of x to the m. But then you put this little dx here. This is just part of the integration process. When you take a derivative, you divide by the dx. When you integrate, you multiply by the dx. That's kind of the idea of the opposite there, multiplying versus dividing. That's why there's a dx in the top instead of a bottom. There's no dy because this thing is basically your dy. Again, don't worry about that confusing idea there. So here we go. Here we go, here we go, here we go. Now when you actually integrate, this symbol is no longer there. Notice above, When you integrate, that symbol is no longer there. You just switch to a capital letter instead of a lowercase letter. So the exponent needs to increase by 1. So we get x to the n plus 1. If we start out with n, we have to add 1 to that. Divided by. Then we are going to divide by what the future exponent is. The n plus 1, this is the future exponent, so that's what we divide by. But then there is also the plus c. So what we're saying here is that little f of x is the x to the n, capital F of x is the x to the n plus 1 over n plus 1 plus the c. Or you could say f prime of x is x to the n, and then the regular function is x to the n plus 1 over n plus 1 plus c. That goes with the above. If I just do this, there we go. My squiggle looks a little off. Drag that. That looks awful. Everything just got squished on itself. I don't want to have that moved. Sorry. I'll rewrite that for the next time. These are all saying the same thing. The integral of x to the n is x to the n plus 1 over n plus 1, then plus a c. If you prefer to call the original function a lowercase f, when you integrate it, you call it an uppercase f. If you were given the original function written in derivative notation, or it could have been dy dx or df dx, then the function would be this. Again, you have to get used to the different ways you can see this. If you're given it originally as a function, the integral is a capital F. If you're given it originally written in derivative notation, then the integral is just a regular function, no capital that time. Check this out. Take the derivative of the right-hand sides. The x to the n plus 1 over n plus 1 plus c. Let's take the derivative of that. So d dx, all of x to the n plus 1 over n plus 1, then plus c. Well, derivative means take the exponent, drop it down. This n is not an x and this is not a variable. These are representing numbers. There's no implicit differentiation here. These are numbers. So we drop the n plus 1 down in front. Then we have to multiply that by the x. We're going to decrease the exponent, n plus 1 minus 1, divided by, now you might notice this is a terrible looking product. We have to wrap it in parentheses. That n plus 1 is still on the bottom. Then there's the plus. The derivative of a constant is 0. The n plus 1's here cancel, so that's just an x. The plus 1 and the minus 1 cancel, so we get x to the n. QED, that means quod erat demonstratum. It means proof, proofed, done, finito, finished. So now that we have our power rule, let's try it out. Again, this right here, this is the main version of it. I'm not going to leave the highlighting there. I'm just highlighting it for a second. Add 1 to the exponent, divide by the same new value, not the original value, the new value. Example 1.
All right, so let's go ahead and take our break. Let's see what I have left. Let's say back at 8:04. we will pick up with that example 1. All right, so let's go ahead and pick up using this power rule for integration. Remember, we're going backwards from differentiation. Integration is the same thing as anti-differentiation. And we're going to try this out with example 1, and then, of course, many, many, many others.
Find the integral of the given f of x. So again, that doesn't say find 5 times f of x times dx. This is the integral symbol. I just want you to go ahead and get used to me writing it a little sloppy because I usually don't take an hour to write that. This is what it comes out to. So for a, I'm going to give you an original function of x to the 5th. So x to the 5th is our original function, and we're going to find its antiderivative. We're going to find its integral. This is the process of integrating or anti-differentiating. They all mean the same thing. So in red, we'll do the integral of x to the 5th times dx, which, by the way, the dx, this is known as a differential. And no, not the differential of a vehicle. No, not a differential like a differential diagnostics in medicine. This is for math differentials. Differentials relate to derivatives. We're going backwards. This right here is just letting us know what the variable we're integrating over is. Kind of like when we had the dx in the bottom, that let us know what letter we were taking a derivative with respect to. So this is kind of like our with respect to. So if you had mixed variables in here, which we can see in later chapters, and we will, it tells you how you're actually processing this. Do you care about the x's or do you care about the y's? All right. So here's what we do. This is a power rule. So the x stays. The exponent, we add 1 to the exponent. That's what n plus 1 means. Add 1 to the exponent. So 5 plus 1. I'm writing out all the detail this time. Divided by. Divide by literally the same value you just wrote. 5 plus 1. But don't forget your constant at the end. 5 plus 1 is 6. So this is x to the 6th over 6. I got a little crazy with that division bar. Plus c. This is it. That's the answer. Or you can write it as 1 over 6 times x to the 6th plus c. Why did that happen? There we go. That's the same answer. X over 6 is the same thing as 1 over 6 times x. My math lab should not care which way you write it. I will not care which way you write it. But if you said it was 6 times x to the 6th, that would be wrong. If you don't believe this, you can take the derivative and you should get the original problem. If you drop the 6 down, so in a different color, and this is going to be the only one I check, take the derivative of what you got as the answer, x to the 6th over 6 plus c. You bring the 6 down, so that's 6 times x. Decrease the exponent by 1, so it's now 5. Don't forget that there was a 6 in the bottom. The derivative of a constant is 0. These 6's cancel. You get x to the 5th. It works. As I said, it's the only one I'm going to check. But you are always more than welcome to check. Let's try another. And let's go ahead and get weirder with this. F of x equals the square root of x. We're going to find the antiderivative of this. Now remember back in the derivative sections when we dealt with square roots? What did we have to do? We never had a square root rule or a cube root rule. We had the power rule. We had to switch this to its other notation. So you need to remember that the square root of x is equal to x to the 1/2. The index becomes the denominator, the numerator is the power originally. So the integral of the square root of x dx is equal to the integral of x to the 1/2 dx. If you don't do that, you can't move any further. So now we apply our power rule. Remember, the power rule just basically says add 1 to the exponent and divide by that same new value. Add 1 to the exponent, divide by the same new value. The exponent is originally 1/2, so maybe you need to say, well, what is 1/2 plus 1? Because that's what's going to be coming up. We have to take that 1/2 and add 1 to it, divide by the same value. Take 1/2 and add 1 to it, but don't forget to add the constant. So there's 1/2 plus 1s, that's 1/2 plus 2 over 2, which is 3 over 2. You've got to be down with your fraction arithmetic or you're going to have problems. So 1/2 plus 1 is 3/2. So this is going to be equivalent to x to the 3/2 divided by 3/2. This is a compound fraction or a complex fraction, depending on what name you like. They're not allowed. So we've got to adjust this. And we move on, right? There's nothing else after this. Wrong. Plus c. So again, as a reminder, a over b divided by c over d. This is the same thing as a over b division symbol c over d, which is a over b times d over c. You flip it and change from division to multiplication. That's how we divide by a fraction. You multiply by the reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. So x to the 3/2 over 3/2 plus c is the same thing as x to the 3/2 times 2/3 plus c. But we don't like a normal product like this to be variable then constant. We want the constant first. So put the 2/3 in the front. This is our antiderivative. This has the x to the side of the fraction. It could also go in the top. So you could go 2x to the 3/2 over 3 plus c. Now, I have these boxed up, but I really don't like these answers. I don't like these answers because the original problem was in radical form. So me personally, I prefer my answers in radical form, but I know that my math lab very often allows this to happen, especially when these are in the denominators. But they're not, so I'm going to say it's much better to switch back to radicals when appropriate. So that says the integral of the square root of x dx is equal to 2/3 times the denominator is a 2, so that makes this a square root. The numerator is a 3, and I'm talking about the power, not the 2/3 fraction. I'm talking about this 3/2. This denominator is a 2, so it's a square root. This exponent's power is a 3, so that's a 3 inside. So that's 2/3 times the square root of x cubed plus our c. This is the best answer. Again, the square root could be to the side or to the top. When I say best, I just mean it's better to have radicals than the rationals. So there's a little more going on with that problem, so let's review. Radicals. Calculus always got to be turned into rational exponents. That's got to happen at some point. Then we apply the power rule, which is said add 1 to the exponent divided by the same value. We did our fraction math. But then because we had divided by a fraction, we had to multiply by the reciprocal. This is an old rule. Everyone needs to know that, which turned this into 2/3 x to the 3/2 plus our c. But then we said, because this is pretty easy to switch back to the original notation, let's do so. So the x to the 3/2 became a square root of x cubed. If this had been x to the 2/3, this would be the cube root of x squared, but it's not, so it's not. So this is a great problem. Any type of radical problem is great. You can handle anything like the 5th root of x to the 9th, the 17th root of x to the 3rd power. I don't know. All those you can integrate. Let's do another one. C. Let's find the integral when our function is equal to 1 over x squared. So we're doing the integral of 1 over x squared dx. So here's the function, and then we have the times the dx. Now, note, this is equal to the integral of dx over x squared. If you multiply the 1 and the dx, you don't really need the 1 in the top. These are one and the same. I don't care which way you write it. You need to understand that they're one and the same, though, because you might see it this way, or you might see it the other way. So be prepared for both. I don't always just give you the function and ask you to do this. Sometimes you're just given the problem straight up. In fact, this is how I usually just go ahead and denote things. I usually don't give you the function and ask you to find the integral. I usually just say, find this integral. I might write it in the left way. I might write it in the right way. And I don't mean right as incorrect. I mean right-hand version. All right, well, we know our power rule. Power rule says add 1 to the exponent and divide by the same value. But here's the thing. Look where that x is. It's not in a denominator. It's in a top. We had the same issue with regular derivatives back in weeks ago. So when the variables were in the bottom, we had to bring them to the top. Guess what we're going to have to do here? You're going to have to bring the variables to the top. So this x squared, when you bring it to the top, you change the sign of the exponent. Excuse me. In fact, I got a cough pretty bad. I'm going to mute for a second. All right, much better. So we get the integral. Now the x squared comes to the top. If it was a positive 2 in the bottom, it's a negative 2 in the top. Do I really need to write this 1 times x to the negative 2? Do I really need that 1? No, so I'm not going to write it. Just going to write x to the negative 2 dx. The dx is always in the top. It never goes to the bottom. Leave it alone. So what we do is, now I'm going to integrate. If you do this, if I do this and x to the negative 2 plus 1, this is wrong because I still have that integral symbol here. This is so common. When I learned calculus, guess what? I did it a couple times. When I'm in class watching students, guess what? Somebody's doing it. When I give a test, guess what happens in the answers? I see this in the answer every now and then. When you actually go through and change your exponents and do whatever formula you're applying, this symbol shouldn't be there anymore. So it's equals. No more snake S thingy anymore, just x. Add 1 to the exponents, that's negative 2 plus 1. Show your work for this because sign math is hard sometimes. Then divide by the exact same thing as the new exponent, which is negative 2 plus 1. And we add our c. Now negative 2 plus 1 is not negative 3. That is the most common mistake people make. It's negative 1. all over. Negative 2 plus 1 is also negative 1. There's a plus c. Dividing by negative 1 is the same as multiplying by negative 1. So we don't want to leave that in there. We generally don't like negatives left in denominators. If this was a 2, you could leave the 2. If it was a 5, you'd leave the 5. But the negative really needs to come in front. Dividing by 1 does nothing. So this is negative x to the negative first plus c. But this is bad notation for an answer, and my math lab generally will not accept this. Negative exponents are not very sane. They're not very normal. You need to bring this variable back to the bottom, just like we were doing with derivatives, and change the sign of the exponent. Now that negative, this negative is still in the front. So that's what I just wrote here. That's the negative. Now this x to the negative 1 is going to become a fraction, and the x to the positive 1 goes in the bottom. We still have our plus c to the side. There's nothing written in the numerator, which means you need a 1. Now this 1 we typically don't write. We typically don't write 1s for exponents because then they look like primes, and I'm not taking any more derivatives or anything like that. This is just the answer, 1 over x, with the negative in front. So negative 1 over x, then plus c. Let me just move that. Equals negative 1 over x plus c. The negative can go on the top, or it can go in front of the fraction. Shoot. So either of these is okay. But having the negative 1 as an exponent, this is not okay. You cannot leave that in an answer. You have to simplify that. Again, if you don't trust this, do the derivatives. Everything will work out and you'll get your original functions. The derivative of the constant will always be 0. The derivative of that primary term will always go back to the original function we had. Now, I need to point out something. The rule that we wrote earlier for the power rule is incomplete. This power rule right here is incomplete. There is a detail that is missing that I am now going to cover. So let's just do an asterisk here. Weird. What happens if we try the power rule on f of x equals 1 over x? So check this out. Integrating 1 over x dx. Bring that x to the top. So this is the integral of x to the negative 1 dx. The exponent was originally a positive 1, so now it's a negative 1. Now we can actually do the integral. We add 1 to the exponent, divide by the same value. So we go x to the negative 1 plus 1 over negative 1 plus 1. Don't forget the plus c, which is negative 1 plus 1 is 0. So that's x to the 0. Ooh, that was terrible looking. Over 0 plus c. Anything raised to the 0 power is just a 1. That's 1 divided by 0 plus c. But anything divided by 0 is undefined. Now here's the thing. There is an antiderivative to 1 over x. There is an integral of 1 over x. But when you try to do the power rule with this, it fails. The reason it fails is because when there was a positive 1 in the bottom, that makes it a negative 1 in the top as an exponent. When you add 1 to negative 1, you get 0, and you can't divide by 0. So this is a problem. The power rule does not apply with exponents of negative 1. When your x is in the top, if the exponent's a negative 1, you cannot apply the power rule. So I'm going to go back to the power rule. You all need to go back to your notes and adjust the power rule. And you need to make a note that the original n cannot be negative 1. the original n cannot be a -1 because when you add 1 to it, you get 0, and then you're dividing by 0, and kaboom, the world blows up. Bad things happen. That doesn't say that there's no antiderivative for this. There's a formula for it. And in fact, if you think carefully to the only 4 or 5 formulas we really gave you for derivatives, there was a derivative that had an answer of 1 over x. We'll get into that shortly, though. We want to do some other problems first. So more on this later. Sooner than later. So right now, all we have is the power rule, and we have one minor exception that the n is not allowed to be -1. There was no exception like this for derivatives because we were bringing exponents down, and that was never going to be an issue of dividing by 0. But when a formula involves dividing by something, it's possible that this bottom could be 0, and that's only possible if the original n was -1, because -1 plus 1 is 0. So that's why there's an exception to this case. Again, we'll come back to what really happens with this integral. We don't use the power rule. There's a formula. We'll come back to it. Again, that formula is spoiled based on the derivatives. But for now, let's talk about the sum and difference rules as well as constants. So constant integration will be here. Remember, if you took the derivative of a linear term, you got a constant. So the derivative of a constant, and I'm going to use the letter a since there's going to be a c somewhere. The derivative of a constant, so the integral of a, and then this is the dx. Again, this is just part of the notation. This is the function right here. That's a constant. A number. A is a number. This is equal to ax plus c, where again, a is a number, as well as c. It's a constant. So the integral of 7 would be 7x plus c, because the derivative of 7x is 7. You can also say, shoot. You can say, shoot. Oh. Forget it. Oh, it worked that time. I don't understand Word. Sometimes that works, sometimes it doesn't. Okay. In general, what if you have the integration of a constant times a regular old function? Remember how when we took a derivative, the constant in front didn't really matter, you just multiplied it out? Guess what? Same thing. The integral of some a times a function is just equal to a times the integral of the function. In other words, the constant is just a multiplier. With derivatives. Now this is super general. This doesn't just say the power rule. This says the integral of any function times a number is just the number times the integral of the function. And we will see that applied shortly. Also the sum and difference rules of integration say, just like derivatives, these do not affect formulas or outcomes. In other words, the integral of some f of x plus or minus a g of x, no matter whether it's a plus or minus, is just the integral of the first function, the first thing. Then you can add or subtract the integral of the second thing. Just like with derivatives, this is not true for multiplication or derivative or divisions. And you know what kind of sucks? While we had a product rule and a quotient rule for derivatives, there's no true product or quotient rule for integrals. We have a lot of different scenarios that we have to kind of be careful with and play our hands appropriately. We will get to that much later. So just like if you have the derivative of x squared plus 5x, you can take the derivatives of those terms one by one. If you have the integral of x squared plus 5x, you can take the integrals one term at a time and just throw in the appropriate signs as needed. Okay, let's try this out. Example 2. Again, find the integral of the provided function. For A. Sorry, my dog is distracting me. Come on, buddy, stop it. The integral, or sorry, let's have our function be 3x squared. Hold on. All right, my dog kept licking my feet. He had to move. Fun times. The integral of 3x squared plus 10x minus 7. There's our function. That's an ugly 2. So here's our original function, and we're doing the integral, not the derivative, the integral. We're going backwards, so using new formulas, new ideas. And you might be saying, why would we ever want to do this? Don't worry, we'll get there. So the integral of, and because there's multiple terms, you have to wrap it in parentheses like so, 3x squared plus 10x minus 7. This could have been how I originally gave you the problem. I can give you the problem written just like this in red, or I can say, find the integral and here's your function. Or I could say, here's your f prime, find f. Or I could say, here's little f, find big F. Those would all be the same problem. So these pluses and minuses don't really affect anything. You can just think about these integrals of terms one by one. The 3 and the 10 in front don't affect anything. You just leave them attached. So you can show the really meticulous work of this, which I will never, ever, ever do again. This is the integral of 3x squared dx plus the integral of 10x dx minus the integral of 7 dx. This is the fancy way of doing things. And then you can bring the 3 and the 10 in the front. So 3 integral x squared dx plus 10 integral x dx minus integral of 7 dx. You don't have to write things that way, though. Most people know they can go straight from the first to the last. So whether you do this writing or not, I don't care. Just understand that the 3 stays there. Then we add 1 to the exponent and divide by the same value. So x to the 2 plus 1. I'm going to keep showing this work for a while. Divide by that same value, 2 plus 1. Then a plus. Leave the 10 there. Then we have our x. Now there's no exponent written, so we have to assume that it's a 1. We don't like writing 1s because they look like primes, though. So we don't write it. So the original exponent was a 1, and we're adding 1 to that. Divide by that same value. Divide by 1 plus 1. Minus. Now this is just a constant. There's no x's. We said up here that the integral of a constant was just the constant times the variable. So minus 7x. And if you stop here, you're wrong, because we need the constant of integration. That's what this C is called, the constant of integration, or integration constant. But we can definitely clean this up some. In the bottom, in the bottom an exponent, 2 plus 1 is 3. In the bottom an exponent, 1 plus 1 is 2. So this is 3x to the third divided by 3 plus 10x to the second divided by 2 minus 7x plus c. The 3 and the 3 here cancel, and you get an x cubed. The 10 and the 2 here divide, and you get a 5. So 5x squared. The minus 7x stays, the plus c stays, and there is our integral. And if you do the derivative of x cubed is 3x squared, boom. The derivative of 5x squared, bring the 2 out, 2 times 5 is 10, 10x, boom. The derivative of negative 7x is negative 7, the derivative of a constant goes away. So again, sums and differences do not really affect the rules for integration. Constant coefficients do not really affect the rules of integration. This is a great simple example to demonstrate that. And remember, if you ever don't like something, if you're not sure about something, when you're integrating, take the derivative. If you get the original function, then you're good. Let's do another. 3x squared. Let me write that this is f of x. I forgot that part. F of x equals 3x squared. Oh, I'm sorry. Sit that one. Flip the paper, Rodney. X to the fourth. Minus 6x cubed. This is what happens when you're teaching with one eye. Plus 5x minus 1. We want to find the antiderivative. We want to find the integral. So what we're doing is integral symbol. Multiple terms, so it needs to be in parentheses. Let me show you what it would look like without the parentheses, in fact. So let me just write, I'll leave the space for it. X to the fourth minus 6x cubed plus 5x minus 1. And then you have your dx at the end. Now this dx is supposed to be multiplied by the whole function. This is only multiplying the dx and the 1. These are the only two things linked together. So this is very, very bad notation, which is why you have to wrap your function in parentheses for integrations if there's multiple terms. When in doubt, use a parentheses. Okay. All these are polynomial terms except for the constant at the end. So all of these, you add one of the exponent divided by the same. For the constant, we just get an x next to it. So with x to the fourth, add 1. I'm going to stop showing the adding 1. 4 plus 1 is 5. So that's x to the 5 over 5. Again, this number and this number should always match when you're integrating. Minus, leave the 6 alone. Have our variable, add 1 to the exponent. 3 plus 1 is 4. Divide by that same number. Plus symbol. Leave the 5 alone. Then we have our variable. Add 1 to it. There's no number written here, which implies that it is a 1. 1 plus 1 is 2. So that becomes 5x squared over 2. Again, these numbers match. These numbers match. These numbers match. Minus the integral of a constant, just slap an x next to it. So 1x. I'll write the 1 here, but I won't in the next step. And then don't forget your plus c. Let's clean this up. X to the fifth over 5, nothing cleans up. That's x to the fifth over 5, or 1/5 x to the fifth. Minus the 6 over 4 reduced to a 3 and a 2. And this would become a 3, this would become a 2. I don't want to leave that written there. So that's minus 3 in the top, 2 in the bottom. Then we have our x to the fourth. Then plus the 5x squared over 2, nothing happens there. minus the 1x. We don't need to write the 1, and we leave our plus c there. And again, you can write it this way, or you can write the variables to the side. So that would be 1/5 x to the 5 minus 3/2 and x to the 4th plus 5/2 and then x squared minus x plus c. Both of those answers are 100% acceptable. Sometimes you'll see things written the left way, some the right way. You got to be prepared for both. Let's do another. Lots of repetition since this is new. Let's have our original function be y to the 4th. Let's and since I'm going to do y's, this needs to be an f of y. Sorry about that. So we're going to do an f of y is going to be y to the 4th plus the 4th root of y. Now, because these variables are y's, when I do my integration, I'm not going to do the integral of dx, even though I know the original instructions said that. We're going to integrate this over dy, just so these letters match. They don't always have to match. We'll get into that in a later chapter. So y to the 4th plus the 4th root of y. Well, we're going to have to change the 4th root of y, aren't we? This is going to be the integral of y to the 4th plus y raised to the 1/4. The 4th root of y is y to the 1/4. The exponent was a 1, the index is a 4, 1/4. All right, well, that's good enough. We can apply the power rule. Add 1 to the exponents, divide by the same resulting value. So that's going to be y to the 4 plus 1 is 5, divided by 4 plus 1 is 5, plus, let me do this work to the side at least for the fraction. So note 1/4 plus 1 would be 1/4 plus 4 over 4, which is 5/4. Come on, select. Why aren't you selecting? That was weird. It's Word. Shouldn't be surprised. So adding 1 to 1/4 is 5/4. So this will be y to the 5/4 in the top and then divided by 5/4 in the bottom. Plus c. Okay. Y to the 5th over 5, nothing happens. But we're dividing by 5/4. Dividing by a fraction is the same as multiplying by its reciprocal. And I'm going to go ahead and put that in the front. So dividing by 5/4 is the same as multiplying by 4/5. Again, this is 4/5 because this was 5/4. Dividing by 5/4 is multiplying by 4/5. We saw that demonstrated back up here in blue. Dividing by a fraction is multiplying by its reciprocal. Then we have the y to the 5/4, then our plus c at the end. Now my math lab might be okay with this. I'm not really, because that 5/4 you need to switch back to the original notation in my opinion. So this is y to the 5th over 5 plus 4/5, that's the fraction in front. Because the denominator of the exponent's a 4, this will be a 4th root, because the power is a 5. The numerator is a 5, excuse me, the power is a 5. And then we have our plus c. This is the answer in the best notation. Remember when we were doing derivatives of radicals, the radical index generally didn't change? Guess what? Still true, because you're adding or subtracting 1, denominators aren't going to change. So if you start with a 4th root, you're going to end with a 4th root. If you start with a 17th root, you're going to end with a 17th root. It's the powers inside that typically change. Now, I'm not going to say there aren't exceptions to every rule, but this is just generally what you'd see. Somebody's got their mic on. If you don't mind, please and thank you.
It's called roses. I'm sorry, roses.
You got your mic on. Whoever's talking about roses. There we go. All right. I muted you. I wish I was able to have everybody be able to talk to me in class, but I know that half of y'all got stuff going on just like me. Fortunately, with me, it's just dogs, and I can make them shoo. So again, the pluses and minuses don't really affect the outcome of an integral. Constants in front of variable terms don't really affect the outcome of an integral. But we said earlier that multiplications and divisions, there's no product rule. There's no quotient rule. You can't just take the integral of the top and the integral of the bottom and slap them together, or the integral of the first thing and the integral of the second thing and slap them together. And you might say, well, let me do the first times the integral of the second, then plus the integral of the first times the regular second, and try and like manipulate the product rule of going one way to another way. It doesn't work that way. Now, what's interesting is one of our techniques for products involves kind of what I just said, but very rearranged. Again, another day. But for now, what happens if we do see a product? So example 3. I'm making this a new example because it's different, but at the same time, it's the same. So we're going to find the integral of f of x dx. And this time, I'm just going to go ahead and write the function inside of it. So here's our integral symbol. And we're going to have an x cubed times 4x to the 5th plus 2x dx. Now, this is written as one big product, so this is perfect notation. I don't have to say, write a bracket around this stuff. I don't have to do that. You might see it that way, but you don't need it. This is fine. If this x cubed had a plus here, then this would not be fine. It's not, that's a times. So this is a product. There is no product rule. So for now, just try distributing. So this will be equal to the integral. X cubed times 4x to the 5th would be 4x to the 8th. X cubed times 2x would be 2x, so plus 2x to the 4th. 1 plus 3 is 4. And then we have our dx here. I distributed, so I don't really need the parentheses anymore, right? That's usually what happens. And yeah, in algebra, that's fine, but now we got this extra little dx thing that is still supposed to feel like a product of everything else, so even though you distributed, you still need that parentheses. It kind of feels unusual, but you get used to it. Such is life, right? Now we can actually apply the power rule. So if this was something that had to be FOILed, you'd need to FOIL it out. If it was even worse than that, for now, you'd have to do that multiplication. Spoilers, again, it's like the 4th time I've mentioned this, later it's not always going to be so clear-cut. We'll have techniques for them. So equals. Now I'm integrating, so I don't write this symbol anymore. I don't need that anymore. I'm going to apply the rules. Leave the 4 in the front. For the x to the 8th, add 1 to the exponent. 8 plus 1 is 9. Divide by the same value. 8 plus 1 is 9. Plus symbol. Leave the constant coefficient in front, so plus 2. Add 1 to the exponent, divide by the same thing. So that's now x to the 5th, and divide by 5. Then don't forget our plus c. 4 and 9 don't reduce, 2 and 5 don't reduce. This is the answer. Does it? You missed the c, you're wrong. If you subtract the exponents instead of adding, you're wrong. If something could be simplified and you don't simplify, you're wrong. Please be careful. You're going to be testing in a few days on derivatives. You are not being tested on this. So when you're doing power rules in this upcoming test, don't add 1 to the exponents. You're going back to subtracting them. When you take test 3 of the final, I can give you an integral, then a derivative, then an integral, then a derivative. You've got to pay attention to the instructions. Pay attention in which direction you're going, because that is extremely important. Don't just think, oh, I'm going to always subtract 1, I'm always subtracting 1, I'm always subtracting 1, or I'm always adding 1, always adding 1, always adding 1. Problem 2 doesn't have to be anything like problem number 3. Doesn't have to be like anything like problem number 4. Pay attention to the instructions. Have your rules in order. Practice, 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 practice. How many hours a week? 8, 9, 10 hours a week outside of the lecture is what you should be dedicating if you still struggle. If you master it in 4 hours, you only got to do 4 hours, right? All right. So that is enough with the power rule. But guess what? We had rules for taking a derivative of exponential and logs. Guess what? We also have rules for taking integrals of exponentials and logs. So let's get to these other types. Oh no. Come on, quit this. Frustrating. I don't know why I can't just insert a page after that. Get it? Draw, erase. Sorry about this complication. I thought I gave myself enough space and I didn't. So this integral was 4 x to the 9th over 9 plus 2 x to the 5th over 5 plus c. There we go. All right, other rules. Specifically, exponentials and logs. Exponentials in the e base, the integral of e to the x is e to the x. This only works if the base is e, just like the derivative only worked if the base was e. The derivative of an exponential was itself, as long as the exponent was just a plain x. We had that chain rule that got involved with it as well, but for now, we're just going to keep the exponent simple. We'll play with that soon enough. In fact, let me go ahead and do that. So this is the first version of the rule. Or the integral of e to the ax dx. We're only going to give you one very simple version of this for now. This would be 1 over a times e to the x plus c. E to the ax plus c. So the first version is if the exponent is just a plain Jane x. Honestly, we won't see that a lot. This version is if there's an extra constant in there. And honestly, this just kind of follows from the chain rule of derivatives. When that happened, you took the derivative of the exponent here. So this is like us undoing it with the division, just like we divided by the n plus 1 with the power rule. So this is only a linear term. If this is an x squared, we don't know what to do for now. If this is an x cubed, we don't know what to do for now. This is just a 5x or a 7x or a 12, things like that. Then for our natural logs, we have that the integral of something, I'm going to leave this something blank for a second, equals the natural log of the absolute value of x, and of course plus the c. And I'm trying to exaggerate the absolute value parts because of the L and Ln. We had a derivative of the natural log of x before. d dx of the natural log of x was 1 over x. So guess what? The integral of 1 over x is the natural log of x, basically. Remember I said earlier that power rule had that weird special case that you couldn't let the exponent be a -1? When the exponent's -1, this is what you fall into. Now that's not the integral of a natural log. That's an integral leading to a natural log. The integral of 1 over x dx, or dx over x, is the natural log of the absolute value. This absolute value is often not written if the problem claims x is bigger than 0. That would make the absolute value pointless to say. If you say that x is positive, you don't need to take the absolute value of a positive. It's positive. But here's the problem. If I don't somewhere say that x has to be positive, we're allowing x to be negative when you can integrate it. But if you remember how logarithms work, you can't have non-positives inside of a logarithm. This x has to be positive, or the inside has to be positive. But if this x over here is negative, if this was just a regular logarithm, now you've got a negative inside of the logarithm, and you're breaking the rules. So this is kind of a weird issue. If the problem says that you're only dealing with positive x values, you don't need the absolute value. But if it's just a very generalized problem, which is more often what you'll see, you need the absolute value. And let me tell you, this is what students forget. Because you don't need it for a derivative, but you need it for an integral. It's subtle, subtle differences. And I would say probably half the time you're told that the x is positive, which means you don't need the absolute value. But then the other half, you're not told that, and you do. So you just have to understand the context. You have to understand when you need it. Me personally, I always use it because even if we're told that the x has to be positive, this is still true. So this is the n equals -1 case. You might say, well, I don't see a -1. It's right here. This is an x to the +1. When you bring it to the top, that's your x to the -1. So when we tried to do that with the power rule, this was the integral of 1 over x. We brought the x to the top. The -1 causes 0 in the bottom, and the world imploded on itself, undefined. Now we know that the integral of 1 over x dx is really the natural log of the absolute value of x, or the natural log of x if x is positive. Integrals of exponentials is as easy as a derivative of an exponential. The integral of a 1 over x is the natural log of x because the derivative of the natural log of x is 1 over x. Let's try these out. What do we have to? Example 4? Yes. And once again, we're going to find the integral of f of x dx. A. The integral of 7 over 3x dx. There's an x in the bottom. There is only an x in the bottom. It does not have any other exponents. This is that special case. This is not the power rule. If this was an x squared in the bottom, power rule. If this was an x to the 5 millionth, power rule. because it's an x to the positive 1 in the bottom, this is not the power rule. This is the one and only one time you can't use the power rule. We have to use the natural log rule. But there's this 7 and 3 in there. If you don't understand that these are just going to be multiplied by the answer, you can show your work and bring them out of the integral. This is me saying the 7 and the 3 do not affect the integral. They're just constant coefficients. But now there's a 1 in the top because the 7's not there anymore. There's still the x in the bottom and the dx. Now, I never said anywhere x is positive, so I need the absolute value. The 7/3 just stays there. This right here, this integral would be the natural log part. So times the natural log, and if I do this, it's wrong. I'm missing the c. I got to have my constant. And even if I do this, it's wrong, because once again, I never said x is positive, so we need the absolute value. Because with 7/3x, your x is allowed to be any number except 0. So it could be -1,000,000. But if you put -1,000,000 here, you're taking the natural log of a negative, and you can't do that. So this is our answer. So let me show you what I'm saying. So I'm going to do a versus, and I'll do this in blue. So let's say the problem was this, 7/3x dx, where x is positive. So then when you integrate, you have your 7/3 integral 1/x dx. And again, if you don't need to show this middle step, you don't have to. Me personally, I go straight to the end. I just say, oh, I have a single x in the bottom. That's that weird exception to the power rule. When I get a natural log, the 7 and the 3 just stay out front. So 7/3 natural log of x plus c. I don't need the absolute value because I was told x is positive. When you put positive numbers in an absolute value, there's no effect. So these are two slightly different versions of the same problem. One has no restrictions, the other does, which means one has an absolute value and the other does not need it. And I believe in my math lab that if you wrote this as the answer to the second one, if you put that absolute value in there, I think they mark it wrong because you're not being specific enough, because they gave you the restrictions you should know to cut that out. So please be on your toes there. Let's do another. Let's do the integral of 1/8x. Now when I say 1/8x, that x is in the bottom. If it was in the top, this would not be the same problem. If it was to the side, this would not be the same problem. If that was an x squared in the bottom, or any exponent, this would not be the same problem. So this is very similar to the last one. If you need to pull the 8 out, you can, and you don't even have to pull it out of the integral. You can do it this way and make your conclusion, or you can do it, some people will just do it this way, 1/8 times 1/x dx. Some people take this extra step. That's fine. It's just extra work though, it's extra writing. That's not an x on the top, that's a 1. Oh my hearts. Dx. And right here, here's that special case again. When you integrate a 1/x, you get a natural log with an absolute value unless you're told x is positive. The 1/8 just stays out in the front. So 1/8 times the natural log, absolute value of x. And if you box this up, it's wrong. What did I forget? Forgot my plus c. So I left that space there. Again, there are going to be ways, there are times when you can find the c. The problems I've given you so far, you can't find them. You have to be given what's called an initial condition. You have to be told some function value under the integral in order to actually find the c. So there are problems where we can find the c. I have not done any of those yet. All right, problem c, as opposed to the integration constant c. The integral of 5 times x to the -1 dx. Now you might say, oh, x to the negative 1, power rule. If you go and try the power rule with this, negative 1 plus 1 is 0. You're going to be dividing by 0 and the world blows up. No. So it's actually interesting. This is the one time where you want the x in the bottom. This is the one and only one time you want the x in the bottom to make it look more familiar. So we go integral 5 over x dx. Negative 1 in the top, positive 1 in the bottom. If you need to pop the 5 out, that's 5 times the integral of 1 over x dx, which is 5 times the natural log of the absolute value of x plus our c. And that's it. D, the integral of e to the 2x dx. We did a bunch of the natural log ones. Now let's do an exponential. So going back above, we said the integral of e to the x is e to the x, just like the derivative of e to the x is e to the x. But of course, the plus c is thrown in. If you have an extra coefficient with your x, you just divide by this value. And again, I kind of gave you this as a leap of faith, but I did relate it to the power rule, how we divided by that number in the exponent. When the exponent was n plus 1, we divided by n plus 1. When this exponent has an a times the x, you divide by the a. All right. So because this has a 2, when we actually do this integral, we need to divide it by 2. So we go e to the 2x. Let me pick my right color, though. So I am integrating. No more integral symbol. And I can't just go plus c. This is wrong. This is wrong. Wrong. Because this 2 is here, I need to divide by that. And if you prefer to write this as 1/2 e to the 2x plus c, both of those are accurate. There's nothing else you can do here. If you don't trust this, do the derivative. When you take the derivative of an exponential with a complicated exponent, it's the derivative of the exponent times the exponential itself. The derivative of 2x is 2. This 2 times this half will cancel, and it'll give you a 1, and then you still have your e to the 2x. It does work. Again, try that on your own if you're not sure. E, the integral of 8 e to the 4x dx. That's a 4. So the 8 doesn't do anything. Just leave it out front. Times. Because the exponent has that 4 there, we're going to have to divide by that same value. We don't add 1 to it. We just divide by that same value because we don't change the exponents of exponentials. So we'll have the times e to the 4x, but then we divide it by 4. Then our plus c. The 8 and the 4 reduce to a 2, though, this time. So that's 2 e to the 4x plus c. So that one, there was a reduction, unlike the previous example. One last one. Oops. The integral of 5e to the negative 3x. Now I might say, oh, negative exponent, bring it to the bottom. Definitely not. If this e was in the bottom, you'd bring it to the top, no matter what the sign of the exponent was. The 5 does nothing. Leave it out front. Because this is a negative 3, that's what we'll have to divide by. So times e to the negative 3x divided by negative 3. Don't forget the negative. Then the plus c. 5 and negative 3 aren't going to reduce, so let's just make that a single fraction of negative 5/3. And then the e to the negative 3x plus our c. Again, if you don't trust any of these answers, take the derivatives. You will get the original functions if you know how to take your derivatives appropriate. about time. All right. So let's do another set of examples and let's complicate things a little. That was example 4. We're up to example 5. And this time I'm going to change how I write the instructions, but it's literally the same thing. I also want this in black. So we're going to say given f of x, find capital F of x. So little f of x for a is going to be equal to negative 4 x to the negative 1 plus 3 x to the negative 2. So because we're told we're given a lowercase letter and asked for an uppercase letter, that means we know we have to do this integral. There's multiple terms, so wrap it in parentheses. Now, what I love about this problem is it's a mixture of the power rule and something else. It's set up to look like it's just power rule, but this is the third time we've come across this. If you add 1 and negative 1, you get 0. You're going to be dividing by that same value, and you blow up the world. So the first term is going to end up being dealt with like that natural log. The second term is a straight up power rule. So this is a mixture of ln's and power rule. You got to know which one's which. So the first one, we want this to look more like the logarithmic rule. So this is going to be the integral of negative 4 over x to the positive 1. Then for the second term, that's going to be 3. You do want that exponent in the top. We can't power rule the first term, which is why we bring the x to the bottom. So that way it's set up like the natural log rule. We can power rule the second term, though. So this negative 4 in the top, all that is a constant coefficient. With an x in the bottom, your integral is a natural log of an absolute value of x. Then plus, leave the 3. And we're going to add, this is going to be a power rule, so we add 1 of the exponent. Please note that negative 2 plus 1 is negative 1. So this 3x to the negative 2, we leave the 3. The exponent becomes a negative 1, that's us adding 1 to it, and we divide by that same value. And then we add our constant at the end. Well, that's negative 4 times the natural log of the absolute value of x. Dividing by a negative 1 just says to change it to a subtraction, so minus 3 x to the negative 1 plus c. But this is not a regular format for an answer. We don't like negative exponents in answers. So this is negative 4 times the natural log of the absolute value of x minus 3 over x. The x goes to the bottom, but not the 3, plus our c. And what I find is fascinating about this problem is, remember how we did derivatives of derivatives? If you integrated an integral, if you integrated this one, this term ends up being a natural log. And we don't even know how to integrate this term yet because we don't know how to integrate a natural log yet. We'll find out later. We can integrate and get a natural log, but we don't know how to integrate a natural log yet. Let's do one more problem and call it a day. I don't want to get into the next section since we're about to test. And I don't think we have to. This is going to be the integral. It's going to be a big fraction, x e to the x, then a plus 1, all over x, and then dx. I don't need a parentheses. I do want this fraction bar to be a little smaller. Didn't need it that long. I don't need a parentheses since this is a big fraction, multiplying the dx. As long as the dx is to the side. If I wrote the dx in the top, I would need the top in parentheses. Well, this looks like a product, this looks like a quotient, and I said there's no product or quotient rules for integration. There's no straight up product rule, there's no straight up quotient rule. Now, last time when we had a product earlier today, like example 3, we just distributed it. So this time when we got a quotient, maybe we should just go ahead and do the division. So let's split the fraction. Oh, and by the way, the answer to A, I said find f of x, capital F of x. This was the capital F of x. I forgot to write that. So this time our little f is the inside and the big F will be the answer. So if we split this up, here's what we get. The integral of x times e to the x over x. That's the first term over the denominator. Then plus the second term over the denominator, the 1 over the x. But now I do need this wrapped in parentheses with a dx because of the multiple terms written that way. Multiple fractions, it looks different. Well, guess what? In the first one, thankfully, because this looks like a nightmare to integrate with the x's there, they all cancel. So this is just the integral of e to the x plus 1 over x, and then all dx. Again, the thing on the left and right is just the notation. Inside the parentheses is what we're actually integrating. Well, the first bit is literally a formula. The second bit is literally a formula. The integral of e to the x is e to the x. The integral of 1 over x is the natural log of the absolute value of x. You're supposed to memorize those. If you box this up and ship it out, you'll get it wrong, though, on your homework. And you'd have to point out that you did that on a test for me to give you more points, because you got to have your plus c. You don't need a plus c for each term, because if you have a plus c here and then a plus c here, those constants can just be added together to make a new plus c. Like pretend that the first c is a 7 and the second c is an 11. Well, 7 plus 11 is 18. Why not just have a brand new c and call that the 18? Adding a bunch of arbitrary constants just becomes a single arbitrary constant. So these are the very basic rules of integration that we will use for the rest of the next several chapters, in fact. We will keep extending on these concepts. We're going to apply this geometrically, just like when we did derivatives. We talked about how it was the slope of a function at any point. These integrations, these antiderivatives, have a very important geometric representation. So if you graph a function, its integral has to do with the graph in a similar way that if you graph a function, its derivative has to do with the graph. Derivative is the slope at a point, and integral is something else when you talk about graphical. We're going to start seeing these things, this little S snake curve, whatever you want to call it, with numbers up here, like you might have this be a 5 and this a 1, and we'll see what happens when that goes on. But for now, we'll call it a day.
And the final reminder of due dates, 3.2 and 3.4 on today, 3.8 on the 21st, 4.1 the 25th, giving you a few extra days on that one. Test 2 going to be Monday through Wednesday. Check out the review in the assignments on my math lab. Remember to share your work and submit it in Canvas. The test 2 will only be seen in my math lab those 3 days, as will the link to submit your work for test 2 in Canvas. You'll only see it those 3 days. 18 questions, 2 hours, no notes, no books, no calculators, no surprises. Email me if you have any questions. I hope this was an informative evening. We will be back working on 4.2 next time. Besides that, take care, have a good evening, work hard, study hard.